So I'm a professor in biomedical engineering, assistant professor in my second year, and I have been working on things like this, which is a modern-day pregnancy test. It's actually electronic, it's got its own battery, it's got a microcontroller. This thing has more processing power than the Hubble telescope did when it was built in the 80s. And we pee on it and we chuck it in the trash, which is a whole other issue. But what if we could use this not just to tell you if you're pregnant, but if you had an infectious disease, if you had cancer, if you had something that was life-threatening. Not that my children don't feel like that some days, but you could do things like nucleic acid amplification on paper with just the components inside this test and a couple of modifications. And so those modifications are what we're doing. Nucleic acid amplification actually is significantly more sensitive and specific than current antibody-based lateral flow tests. And so they have the advantage of being able to detect as few as single or tens of copies of DNA or pathogens. Right now, there are nucleic acid amplification tests that can be done ostensibly at the point of care. They come in an instrument that's about this big, and they have cartridges that cost about 30 bucks each. And the reason that these cost so much is because they're made out of injection molded plastics. And there's a lot of pieces and parts to them. If we could translate them to a piece of paper, then they would be significantly cheaper. We can use the same types of technologies from roll-to-roll printing that we use to make newspapers for pennies on the dollar. And so that's exactly what we're doing. We are printing both the amplification reagents themselves that can be switched out for any particular gene target. We've been working on cholera for water disinfection and detection technologies. We've been working on sepsis pathogens in blood. And then the real innovation comes from being able to stop and start fluid flow in these little pieces of paper. Nucleic acid amplification requires you to capture your pathogen of interest and then incubate and hold that reaction there for about 30 minutes. Sometimes longer. We've gotten it down to 15. But you can't just have a lateral flow assay that just flows the whole time. So we have printed wax valves that stop the fluid. And then when we want to start the fluid flow again, we can heat them, and they open to allow the fluid to go downstream to a lateral flow test, which is as easy as detecting on a pregnancy test. And so our solution to developing an automated low-cost molecular detection that can be done at the point of care for the patients that really need it, where you don't have to send your assay out to a laboratory and wait for a week to get your results, and may or may not be able to access your patients.